Okay, so the next talk is by Professor Soham Biswas from University of Guadalajara, and the title of his talk is From Classical to Quantum Stochastic Process. Professor Biswas, maybe you can start sharing your screen.
Yes, let me try to share my screen. You can see it, right?
Yes, we can see it.
Okay, so you tell me when I start.
Yes, you can start immediately.
Okay, thank you. First of all, thanks a lot for giving me the opportunity to present one of our recent work. And congratulations, Deepak and Mustansi. So let me start. So today I will talk about the classical to quantum stochastic processes. So this is a very recent work, which is now in archive, and we are in the journal also. So my collaborators for this work was Thomas Godin and Gustavo Montes. So, okay, so what is a quantum process? In case, okay, here we are talking about the dynamical systems only, and in the quantum processes, in quantum systems, it have been characterized by superposition principle and coherence, whereas the classical process that have been characterized by the random choices and stochasticity. So people have been asking this question that what will be the correspondence between the classical and the quantum processes. So till now, for the traditional approach from the point of view of open quantum system, which have been done this way, that people start from a unitary quantum process of an isolated system to find out the related classical stochastic process by measurement and by coupling to the environment, gradually replacing the coherent superpositions by stochastic mixtures. On the contrast, our approach is now to start from a given classical process, ask what are the quantum processes that can be converted to that specific classical process by repetitive projective measurements. So let's look at the stochastic Markow process from classical to quantum. So we will restrict ourselves to stochastic Markow process only. So the classical stochastic Markow process in discrete space and time that can be described by this equation given in the red color, where Pn is the evolving probability vector starting from our initial configuration, and Jn is the stochastic transition matrices. So these things tell you actually what is the probability to find out the state at time n, given the probability of the state at time m-1. Then now we can define the corresponding quantum stochastic Markow process as lambda q, which will be basically defining by a sequence of quantum maps, lambda qn at time n. And all these maps are CPTP maps, that is completely positive trace preserving maps. So if we take these CPTP maps, so this rho n, which is now this density matrix, that will be given by this equation. Okay. Now we can define now before constructing these quantum extensions of this case corresponding quantum process for the given classical process, let us try to understand what is the classical stochastic process in the formalism of quantum channel. So for that, we define a Hilbert space, a space of linear combination of the classical states. Now, once defining this Hilbert space, the ensemble of the classical state will be described by a diagonal density matrix over n. And then we can define a valid set of Krauss operators, which is given by this, okay, which will define a sequence of quantum channels from the definition of the Krauss operators, from the sequence of quantum channels, which will be given by this rho bar n equal to lambda jn rho n minus 1, where this lambda jn, this is basically the classical transition map. And this is how we define the classical stochastic process in the formalism of quantum channel. Now, what is a quantum extension in our definition? So a quantum process described by a sequence of classical quantum maps, we will call it a quantum extension for that classical process described by lambda jn, if and only if for all n, we have this equation lambda jn, which is p composition lambda qn composition p, where p is a complete measurement of the set of classical states j. So we try to explain these things by this picture. So let's say this is a 3 time step quantum process defining by this lambda q. And now which is given in this line A. Now we actually include the complete measurements denoted by P, just before and after each quantum map, which is given by line B. And now if we duplicate the intermediate measurements, which is given in line C, then finally we reach the classical stochastic process, which is given by lambda J. Now, basically, we have to find out the lambda Q, which is the quantum sum extension of the quantum process corresponding to the classical stochastic map lambda J. For that, the guiding principles are as follows. So we have to find out this quantum extension for each stochastic map individually. For that, for the corresponding quantum map, replace the random which path decisions by the superposition of all available options. Eventually, such superpositions violate unitarity. So we have to find out the orthogonal subspaces such that the unitarity can be achieved in each subspace. So once we define a valid quantum extension lambda Qn, which is a local map, then we define a whole one parameter family of interpolating extensions by the convex sum 1 minus p lambda Qn plus p lambda Jn, where lambda Qn is your local quantum map and lambda Jn is your classical stochastic map. Okay, so once we make this construction, we will try to test our procedure by taking some classical stochastic process. And for the choice of this classical stochastic process, our candidate is the zero temperature Glauber dynamics. For the zero temperature Glauber dynamics, we have a one-dimensional chain of Eisenspin systems. We randomly select a spin. We flip the spin if the energy decreases. We do not flip the spin if the energy increases. And we flip the spin with probability half and remain in the original condition with probability half. That's the random choices if the energy doesn't change. So let's say that JQ is a 3-spin classical stochastic map where Q is between 1 to n. N is the system size. So lambda Qn, that's the corresponding local map operating on spin Q, and then your quantum extension will be the uniform mixture of all these local map. Now, if you think about the Hilbert space, so there are two things happening. One, both of the spins up, that is one, and the central spin is down, or the vice versa, that is 101 or 1010. And in these cases, the spin will definitely flip. Or in the other, there are other cases where 110 or 001, where the spin will go with probability half with either up or down. So basically, we have to separate the Hilbert space into subspace spanned by the states 101 and 010, and its complements. So the projectors that will be P. This will be these states 101, 010, and its complements. So we can construct the local quantum map by this one, where the first term is basically to tell you about the definite flip of the spin, and the second term, which is basically which is basically the superpositions of these random choices. Now this UX that can be decomposed in orthogonal sum like this, where X can be replaced by either an Hadamard gate or either the Hadamard gate or an SU2 matrix, which is given by this color red and color blue. So this is the full construction. So then we simulated this system for until the 20 qubits. And here are the results. So we basically measured the different things. So one of the measurement is the coherence. And we see that the coherence initially increased exponentially, and then it decreased in again in that exponential pattern for the initial time and the late time. We have been able to do the scaling laws for the late time of the coherence. One thing I would like to mention here, that the coherence is low with respect to the dimension of the Hilbert space. So it's so low such that it is not, you will imagine that it is not sufficient enough to affect any classical measurables. Then we study the relaxation time, and relaxation time is the probability to find out the system at equilibrium after time t, which is given by these probability equations, where my equilibrium state is either all up or all down. And then we report the half-life, which is given by this, that is, what is the time the half of the elements will reach to that equilibrium state. And then we have seen this black color, black one, this is the classical state, that is after putting the complete projective measurements. Now this is a t half by n square with plotted with the number of qubits. So this black line should be a straight line, which is not because of the low system sizes. And in the top one, this is red and these magenta lines with the square points. These are the Hadamard. These are for the Hadamard extensions, Hadamard gate. H0 is when you do not do any measurements, and H1 is the Hadamard extensions using the Hadamard extensions using the Hadamard gate, where you do the measurements after each Monte Carlo step.
Professor Biswas, you have 2 more minutes.
Okay, sure. For the bottom one, we have this SU2 extension, the quantum extension using the SU2 matrix, where the magenta one is for when you do not make any measurements, and the red one is when you make the magenta one is when you make the measurements each Monte Carlo time step, and the red one when you do not make any measurements. So you can see they are different from the classical one, and the SU2, this quantum extension following the SU2 matrix, that is faster than the classical one. So thank you. That's all I have to present.
Okay, if there are any questions.
Yeah,
yes.
I wanted to ask, you have said that eventually the unitarity gets broken, but either it is broken very little even in the beginning, or by continuity it will not get broken at all. Is that true?
No, unitarity. Okay, there are 2 things, right? One, there is a deterministic decision, another there is these stochastic decisions. So the unitarity as a whole, the unitarity is broken. The system is not unitary. So we have to achieve the unitarity by dividing the Hilbert space in subspaces. So the system is unitary in each subspace, but as a whole, it's not.
Okay, thank you.
Okay, Obishekta?
Yeah. So I just to make sure I understood, I mean, so what you're saying is that for any classical sort of Markow process, you can find a corresponding quantum process consisting of unitaries plus projections.
Yes.
But it's not a unique construction, right?
Yes, the Krauss operators are usually not unique. That depends on the basis. So for the given basis, if you change your basis, your Krauss operator changes. So all you have to find out is the corresponding Krauss operators, and the rest of the construction follows.
Okay.
So
and
basically
then
there is.
Yes, sorry, go.
Yeah, basically you can show that that's not have been done, but one of the ideas is that you can generalize you can give a generalized prescription of the Krauss operators where all different kind of possibilities of the Krauss operators.
Okay, right. And the other question was, so now the quantum case, one also has the off-diagonal elements. So this has some extra information, right? The
off-diagonal elements are telling you about the coherence. Okay, but all we have started with a purely classical state. That is, our starting density matrix is purely diagonal, which have only, for a specific given cases, which have only one element, one diagonal element. That's from what we start from. If you think about a specific case, but otherwise you start with the ensemble of the classical states, which is purely diagonal. So no, we didn't. But one can, for following this construction, one can also start with cases which have the non-diagonal elements of the density matrix. But as our purpose is to start from the purely classical process to go find out its quantum extensions, that's why we always start from a purely diagonal density matrix. But you can start with a non-diagonal density matrix also.
Okay, thanks.
Tridib, you had a question?
Yes, I had rather one elementary question. So when I see a quantum and a classical process in, let's say, in the Schrodinger equations and the Fokker-Planck equations, the difference is in the measure for the probability, right? So in classical, it's just the probability vector gives the probability, and in Schrodinger, it's the psi star psi. So when you have trying to define a quantum correspondence of a classical stochastic process, how do you see this difference? the difference in the measure of probability?
Okay, so usually, as I was saying, that from the point of view of open quantum system, these have been studied quite a bit. But what people did there, they start with an unitary quantum process in an isolated system, and then they then they couple the system with the environment and try to measure it. Now the stochasticity, they gradually replace these coherence superpositions with the stochastic mixtures. So the stochasticity in case of the quantum theory coming from the measurement theory of the quantum mechanics. Now, what we do is exactly the opposite. We ask the counter question that if a classical process is given, then can you find out a quantum process corresponding to that specific classical process? And that quantum process we are calling quantum extensions.
Okay.
Does that answer your question?
Not with its entirety, but I will ask you during the breakout session.
Okay.
Thanks.
Okay, so if there are no other questions, let's thank Professor Biswas once again, and we'll move on to the next talk.